Znaczy, można nagrywać, prawda?
Okay?
Można nagrywać.
Tak, tak, tak. Okay, let's start. Go. It's okay?
Yes.
All right, good. Okay, great. All right. So the title of my talk is in French, but it is self-explanatory. Okay, and also the image here is sort of self-explanatory. These nice quantum waves propagating curved space-time. That's exactly what this talk is about. And its work, it's actually that the talk is based on my work with Benazou, who's now at the University of Edinburgh, and like a paper which was posted like 3 months ago. Okay. Okay. The motivation for this work is the motivation for this work is to understand the effects of curvature and particle collisions. And what is most interesting is actually what is the behavior of how elementary particles behave in curved times at very low energies, because that's the only case when you have at very low energies, and which is of course necessary. We have a very light particles. Those particles can have wavelength which can reach the horizon and can really be sensitive to the curvature. Okay, so of course we do not expect curvature affect experiments, let's say at Large Hadron Collider, because you probe very short distances and time intervals. Okay, and while when you have particles which are soft at very low energies, then the physics can be affected by the curvature. Now, to understand really those effects at quantitative level, you have to construct the scattering matrix. You have to consider the scattering of particles, and then to see how S matrix behave at low energies. But in general, you have to start from general construction of S matrix curved space-time, and that's complicated. It's something which has been done many times before in a very different context and in many different ways. So what I will present today is some type of new approach which seems to avoid all problems which were encountered before. So now, how we construct S matrix in quantum field theory and Minkowski space and flight space-time? Even when you read a textbook on quantum field theory, you don't even think about, for example, who is making observations, because who will be measuring the scattering, some transition after the compute, you automatically observe, you automatically assume that you are inertial frame, okay? And so the S matrix is constructed by inertial observers who enjoy Poincare symmetry. That's absolutely crucial. Without that, the quantum field theory, would look completely different. And in addition, of course, so when I'm talking about inertial observers, in standard quantum field theory, you do not accelerate observers, because then, of course, you have a particle production, you have all this stuff, but it's not discussed in quantum field theory textbooks. Okay, so the fact, absolutely crucial, property, crucial assumption that you make in Minkowski space-time, that what you do is essentially, it's done by inertial observers. And all those inertial observers are related to each other by Poincare symmetry, okay? If just missing a part of Lorentz group of Poincare symmetry would sort of make connecting all these observers, it wouldn't be possible to connect observers, okay? We have to do computations for different observers. So really they need this maximal symmetry, okay? Now, so we need this number, this maximum number of symmetry generators in order to connect observers. So in general, when you go to curved space-time, of course, you lose symmetries, okay? And then that's essentially the main problem that you encounter, that you deal with lower symmetry. And then, of course, when you do some computations in curved space-time, you ask always the question, who is actually measuring, what am I computing, who will be measuring it, okay? But there's one exception of curved space-time, which is de Sitter space-time, which has maximal symmetry, okay? And with as big as Poincare symmetry, it has a little bit different structure, as you will see later. We have simply the rank of the group is smaller and so on, but the number of generators is the same. This means that all geodesic observers in the Sitter space-time are connected by the Sitter transformations. So that's and that's absolutely crucial, so that will avoid this problem of being forced to single out some observers or single out some reference frame, because all observers will be equivalent. Okay, so that's the basic thing. So by using that, that's the way we will go. Of course, the difficulty when you go to the Sitter space-time, that this group will be, as mentioned, the Sitter group will be different, and the causal structure will be different in the Minkowski space-time. So these are the problems that we are going to face. Okay. Any questions at the time? Yes.
Do you know if any such coordinates exist in the space-time, which is transparent for all four symmetry? Because normally you think about the embedding of the Sitter in 5-dimensional.
Yeah, then I will be using that. Yes. Yeah, everything that I will say at the end should be independent. Or let me go ahead and explain what I'm going to do. Yeah, nothing will depend on of course, at the end, nothing should depend on the way I parameterize the Sitter space-time, yes? Of course. Okay, so that's the end of what should happen. Well, be some mild assumptions about the choice of good coordinates. Okay, no, it's okay. It's okay. Okay, so let me just remind you some basic things about the Sitter space-time. As you mentioned, to construct d-dimensional when it is space-time, so together when d means space and time dimensions, so it's for physical is d equal 4. So we start, the best way to construct the Sitter space-time is to start from Minkowski space-time with one more spatial dimensions, okay? And so in this Minkowski space-time, you have what you do. You choose a surface subject to this hyperboloid constraints, and that automatically, okay, the surface defined by this equation is de Sitter spacetime, okay? And you can find that this curvature, constant curvature, is related to the radius of the throat, okay? Now, this constraint has O1D Lorentz symmetry, which is generated, essentially, it's inherited from Minkowski spacetime. Yes? So, and this is actually this de Sitter symmetry. Okay? So it has the same number of generators. For example, in 4 dimensions, you have 6 Lorentz generators and 4 translations, altogether 10 generators, and the same thing in O14 has the same number, has the same dimension. Okay, you have same number of generators. And those generators, what they do essentially, they are boosts and rotations and embedding Minkowski space. There's another property of that, which would be important later, of this hyperboloid, is has like mirror symmetry, which connects points on the antipodal sides, as I would say, of this hyperboloid. Now, the discussion that I'm going to present is you could do it in any number of dimensions, but it's really much simpler to discuss it in 2 dimensions, okay, where you have the hyperboloid is exactly what you see here, okay? So this is a 2-dimensional spacetime, which has this 2-dimensional hyperboloid. All right, so then the symmetry is O12, which like 3-dimensional rotations with 2 non-compact generators. Okay. All right, and now next thing, which I would, again, to follow that line, have to talk about observers, okay? Because that's very important, okay? It's absolutely, when doing any computations, okay, then some computation physics, so your goal is to compute some observables measured by observers, okay? That's something which is often forgotten. For example, when constructing wave function of universe and so on, you really don't know who's measuring those things. And so that can lead to confusion. It's very important to, when you do physics, when you do computations, to state, to know who is really going to measure it, okay? It's supposed to be physics, okay? So now, so let me talk about observers. These are observers who are freely moving, okay, in de Sitter spacetime, okay? Now, actually, so they are moving along kind of like geodesics, yes? And well, geodesics in de Sitter are as simple to construct geodesic on this hyperboloid as simple as to construct as geodesics on a sphere. What you do is just slice it by a plane, okay, like that. And that in that case, in the hyperboloid case, cuts out 2 lines, okay? And now you can have, of course, this plane can be at an angle, have any normal space-like vector, and actually, by rotating this plane, you can construct all possible geodesics. But it's very important that each geodesic comes with a mirror partner on the other side. Okay? So always 2. Okay? On a sphere, you slice it, you have one circle, one big circle, yes? You have 2 geodesic, okay? Which are on the on the which are related to each other by this x goes to minus x symmetry that I mentioned before. Okay, so for example, so of course, now all these, I say, all these time-like geodesics are related by the set transformations, so you can make always this plane vertical. Yes, and then if you look from a sideway, you have two geodesics on the opposite sides. Okay, and of course they'll be related by this x goes to minus x symmetry, and we will think about it like you will see later that the way I will think about it, when you have a observer which will be moving here, the red observer, the other actual observer, which is observer moving to the future, I will think also about its mirror partner, but it will mirror partner, which will essentially CPT conjugate, which will be backward in time on the opposite side. So what I will do, this parameterization that I will use for geodesics, that the proper time goes to the future, this Minkowski space on one of them, and the proper time, I count it on the other side, it flows in the opposite direction. Okay, you will see that that will be important. So we look at the Penrose diagram here. So we have, for example, you can use these coordinates, the standard coordinates, which I will explain later. And then, so we have always one very important, of course, property that when you use constant time slices, okay, in this case, are circles or in general spheres, yes? And so on the Penrose diagram, I have this red geodesic looks like here, and then the green one is on the other side. And now again, by shifting proper time, I can choose the observer to be here, yes? Okay, by just setting clock. So the same thing as any well, if this I'm talking about Minkowski space, any observer anywhere, an edge observer can be identified with me now. Okay, so the same thing is exactly the same thing. So every observer can be put by this transformations, and so then clock it can be here, and then the other one will be here. Mirror partner will be here, and this one I talking will be proper time will be running here, and proper time will be running on the other side in opposite direction. The other side means here it means that the range of on one half of this hyperboloid corresponds to azimuthal angles between 0 and pi, and then from pi to 2 pi. Note that these two observers, okay, here and here, they could have never been in causal contact. Okay, as you see it here. That's why I draw here. That's why I'm drawing here the Penrose diagram. Okay, but they are completely disjoint. Nobody knows. Okay, this guy could have never communicated with this person. Okay. It's very important. All right. All right. So that's so we have observers, and now yes. Is what?
It's an assumption because you assume that you take a total secret space as a manifold. You can actually take a elliptic in the secret space in which exactly parts of equal parts, so that you don't have this effect. Geometry is exactly the same, so the oncometric observers, geodesics are exactly the same. However, you don't have this double.
No, I'm confused.
The graph, you can actually cut it off. Just the left part at pi, if you like.
Yes.
And it's
So
completely decoupled from the rest. So you can consider that the secret field theory on just on one half.
yeah, but this is one half. This is the one half. As this is as you see from this diagram, this is all what this observer here, who is here at this point, could have seen in the past and can communicate in the future is within these cones. So it is any observer. So in other words, I can go to any reference frame and I can redraw it. And then for any observer, I can redraw the same thing. Because everything here is is connected by group transformations. Yeah.
My point is that, as you mentioned, there is this X marker, there is this mirror symmetry.
Yeah.
And what you can do, you can actually divide by this mirror symmetry and just get a half of the space with the same local geometry, but with different global structures.
No, that will actually, if I understand correctly, that will break the Sitter symmetry, because then the modes, actually you will have, you will see it will, okay, the next thing that I will do, I will discuss the representation of the Sitter group. And you see that in a pose and in that way, well, naturally, if you go to a mod out by X minus X symmetry, you would have to have periodicity. You take only periodic wave functions which are periodic. So it means that will put a restriction on even momentum or angular momentum. Okay.
I'm just asking that because some papers on elliptic Sitter space, I think, and probably about some papers, I don't know, 20 years ago, in which the people exactly half of it.
Yeah. Okay. I just don't want. It may be that it is somehow related to that, but I'm not sure because of that modding it looks to me that would break. That would somehow break the. Huh?
The other observer would have you have to cut the other part of it. The cutting works only for one observer.
Yeah, because then it would have essentially then you would impose only, you have to have if you look at the decomposed wave functions in the modes, then you would have to have periodic conditions from here to here. That would restrict to have it. That means that the modes that you would take only would be the even modes. Okay, because odd modes are not periodic from here to here. Okay, and that would from the states, the corresponding states, I would cut out certain states from the representation of the Sitter group. Okay, so then it would. Okay, that could be one way of talking about it, but that's not the way where I want to go. Okay. So you have observers now. The second thing is to construct the Hilbert space. Yes. Now, and again, in Minkowski space, times the representations of Poincaré group. Okay. So we know that a nice thing, for example, you can talk about free particles with, let's say, all with which are were characterized by all, for example, 4 components of the momentum, energy momentum. They are all commuting. Everything is perfect. Okay. Now, this is, however, different in the Sitter spacetime, because when you take, let's take this 2-dimensional Sitter, then you have essentially like SO3, non-compact SO3 group. It's essentially equivalent to this one is equivalent to SL2R. Okay, and you have 3 generators. And well, we have a non-trivial algebra. Well, it's like SU2 algebra with 2 non-compact generators. So you can choose to construct representations. You can the only quantum number that you have available to characterize the states in 2 dimensions are one. Let's say it's this one operator, which is L0, like this. Like you can take it like a angular momentum operator, and then you have the other one, raising lower operators, so to construct representations, the first thing that you do, you do same thing as for SU2. Well, you have in this case you have only one Casimir operator. Okay, it's a quadratic Casimir operator, and normally it's the values of that for SU2, you take L times L plus 1. Yes, here you take delta times 1 minus delta, and this actually the parameter delta is Well, it's in this case, it's complex. We're talking about non-compact group. And actually, its values are restricted by the unitary representations. But the punchline is that these representations, by labeled by the Casimir by the Casimir values, parameterized by this delta, which is often called also dimension because of the relation of this group, the conformal group, and just the value of L0. Like third component of the spin and the spin value. Yes. Okay. So these are eigenvalues of L0. Now, these different values of this dimension delta corresponds to different type of representations. As I said before, they are constrained by the unitary requirement. And the one which is important for my discussion, which at the end will, the only representation which allow of particles who are arbitrary high masses are the representations which have this angular momentum of dimension, which is 1/2 plus continuous imaginary part. And this representation is called the principal series, from something which is called principal series representation of the Sitter group in 2 dimensions. Now, when you go, of course, to here you see one thing, that if you go, of course, to higher number of dimensions, okay, constructing this representation won't be as simple as this SL2R, okay, but this is actually something which was, the problem was solved long ago by French mathematician Jacques Dixmier in the early 60s, okay, in case of 4-dimensional, the Sitter. And then usually you have the same pattern, like, for example, like in a Poincaré group, yes, you have the same thing. You have all in 4-dimensional, the Sitter, you have 2 Casimir operators. One will be essentially this L square, another one which will correspond to something which could be like internal spin, and okay, and then okay, but essentially everything goes through, okay, and again you will have a principal series which have dimension which will not the 1/2 plus I nu, but we have 3/2 here in 4 dimensions. But the concept, as far as conceptually, is exactly the same thing. It's just becoming more involved when you go to higher number of dimensions. No, how to go to Poincaré? It's not, no, the thing, okay, what happened? I will talk later. What is the, what I mean by what I would call a flat limit, okay? And how you go towards, how you, starting from the Sitter group, how you can obtain, how can take a flight limit and obtain representations of Poincaré group, and this is called new-Wegener contraction. I won't talk much about it. Yeah, but that discrete series and so on. But it's, actually, for example, here you have a separate representation with delta equal 1. That is actually a type of a Carré representation in 2 dimensions. Delta equals 0 is trivial representation, and so on and so on. I have discrete series. Okay, but that's not something that, let me just stick to the principal series, because then I have this mu actually will be related to the mass. Okay. All right. Okay, so next thing, okay, so we have observers, we have states, and now we want to construct quantum fields. Okay. So we construct quantum fields. For that, of course, we want to construct a free field, which will be solving Klein-Gordon equation. And for that, it's convenient to use some coordinates. Of course, very important thing that you have to cover entire the Sitter spacetime. And one of them are so-called global coordinates. And Okay, this is something in 2 dimensions that are particularly simple. And so it's like some conformal factor times the flat metric. There's the same, you can use similar coordinates in higher number of dimensions again. Now, and then what you do, to solve Klein-Gordon equation, you just decompose into modes, okay, into periodic modes with this n is, I can't talk about winding number. Okay, no, n is you can like angular momentum, or actually it's like a momentum in the Sitter space-time. Okay, of course it's quantized because spatial dimensions are compact. Yes, so we will impose periodic boundary conditions, and it's going to serve, for example, into dimensional. So we have these integer modes, and then you solve, and then you proceed and solve Klein-Gordon equation. That's very simple. Okay, actually we have a Klein-Gordon equation. Again, let me assume also that one more assumption that the mass of the Klein-Gordon square is bigger than 1/4. Okay, and then actually I will define this parameter mu, which we identify with this dimension of the corresponding representation. Okay, so this mu will be related to the mass in this way. So this is relation. So you see that only when you have a large mass that corresponds to large parameter mu. Okay, and so mass is related in this way to dimension delta, and the Klein-Gordon reduces essentially to, after some work, to a Legendre equation, and you have 2 solutions as usual. Yes, a second order differential equation for each mode n. So these are solutions allowable by n, and additionally we have this parameter mu, which is fixed, which corresponds to the mass of the particle, and you have then you can have and then the solutions you can write wish anyway. Usually, for example, here they're written as some type of Legendre general they're called not generalized. They're called what Legendre? Associate? No. The Legendre function. They're Legendre like Legendre polynomials. Yes, but with just with huh? Legendre. They're Legendre. Yeah. You can write it as you can write it whichever. These are actually these, since the argument here is between 0 and 1. These functions are called Ferrer's functions, and they are constructed from these general Legendre functions by taking. So they have this generalized Legendre functions have complicated complex structures. You have to take there's some cuts and you take some limits. Okay, but you can use whichever. You can use. You can write them many ways. For example, you can relate to Gegenbauer functions and so on and so on. Okay. Now, but you have 2 of them. But now, so this is good solving. But now, what you need to proceed further in quantum field theory, you have to identify positive and negative frequency modes. And then positive frequency modes will go with annihilation operators, and negative frequency modes will go with creation operators. That's a very important thing that you do in quantum field theory book. Okay. So now, but these are not just. But what you saw here are not just plain waves. Okay. So what the only requirement that makes sense they can impose that. When you go to the limit of large n, which corresponds to very short wavelength, these positive and negative frequency modes should behave as in flat space-time. Yes, and in general, the way I will be reaching flat limit will be simply I will see flat space-time when I'll be probing short distances and short periods of time. Okay, so I impose the constraint now, before quantization, that when n goes to infinity, I will have, okay, I want to have these oscillations with positive and negative. Huh?
You take the you choose 1 point and
I 1 point, exactly.
space to the seeker and one.
No. My requirement is the observer. Okay, there's one observer. I'm singling out, so the whole thing is, he's constructing, he's solving Klein-Gordon equation. Okay, he will choose what is, he will have in his neighborhood, will have a positive and negative frequency modes. And I do it for particular one observer, because everything will go through. With all observers, I can repeat it. Okay, you can always, all observers are related to each other by the set of transformations. So I can talk about one. And this one observer wants to have just positive and negative frequencies and split the solutions in this way. That limit that n goes to. No. Okay. In other words, when I construct S matrix, the one thing which I will always insist, when you probe for processes which probe short space-time intervals, the S matrix should be the same as in flat space-time. Okay, so that's very crucial. That's absolutely a crucial requirement. All right. Yeah.
Couple here with students, because on the one hand, n is dimensionless in the definition of phi. On the other hand, the n should have dimensional mass in the definition of omega. So essentially, and the only dimensional scale you have here is the curvature scale, which means that the n is essentially scaled in the units of the curvature scale, which essentially tells you that it's n going to infinity limit. Means that I would say means that the n is that the distance, relative distance, physical distance is actually much smaller than the curvature.
Yeah, that's what it is. Yeah. Yeah, this is exactly what. Yeah, that's that. What for here I set when here from the very beginning the units were set to be one. The L was set to be 1. Yes, so that it doesn't appear here. So of course, as you say, n is of course the momentum will measure in units 1 over L and so on and so on. Okay, so that you can formalize. Okay, if you see it if you do in a new Wigner contraction, in which you will see that, for example, if you scale appropriately momenta in the limit when L goes to infinity, then momenta start commuting and so on and so on. But that's not something that I want to follow up. Anyway, so these are two solutions, which I would call positive and negative frequency solutions. Okay? Yeah, of course, you normalize them. Or you normalize with a Klein-Gordon norm. That's perfectly okay. That's the standard thing. And that you will see lead to, okay, that will, of course, lead then to properly normalized states. Okay?
Many functions
Yeah, so we normalize these factors here. So, of course, the normalization factors are fixed by, so we have you have, first of all, you have this relative sign between the two Legendre, which gives you something proportional to, so this is actually, this combination can be written as another special function called Meller's function, okay, which, Meller, who was actually in, not Wejherowo, but from W, somewhere in Pomorze, okay? Okay, long ago. Okay, so then normalization is fixed with respect, normalization, Klein-Gordon normalization.
Normalization is always product, so you can rescale the guys by some related factors, no?
No, these have norm equal, or both of them have norm 1. Yeah. Okay. All right. All right, good. So now, of course, we write this, we write a general field, we split it into these positive and negative frequency modes, and one of them becoming, then this coefficient becomes a creation operator, and another one annihilation operator. And then, as usual, then you construct states. Okay, then the first thing, you define the vacuum. Okay, the vacuum, you find the vacuum, is the vacuum which was annihilated by all these annihilation operators. So it's a unique vacuum. It's a unique vacuum. It's very important. There's only unique vacuum here. Usually when people talk, the one thing which when you talk the zeta space-time, you talk something which is called alpha vacua. Again, you have this alpha vacua because essentially you allow not only inertial observers, but you allow all accelerator observers. So then, of course, the things go wild, and you can have various vacua. Now, for this observer, okay, we have a unique vacuum, and that actually this is the zeta group invariant vacuum, as you will see later. And this, which is essentially the vacuum which is annihilated by annihilation operators. There's only one vacuum state. Okay, but before I go to that, to the construction of Hilbert space, let me tell you a little bit more about this wave function. This is really interesting. Okay, they have interesting structure. I told you that in the limit, when n goes to infinity, yes, when the large momentum, they become just simple oscillators. Okay. Now, however, you can look for what happens for finite n, for finite momenta. They are very interesting. First of all, so you can look essentially at the frequency spectrum of these solutions, and you see that they are highly oscillatory, and then they. Now I'm taking n here, which is much bigger. There are two parameters here, which is mu, which will relatively be mass, and n is the limit when n is big. So you call it's like relativistic limit, yes, when the momentum is much bigger than the mass, yes. And I'm looking there at the frequency spectrum, and you find this, and you see that it peaks roughly when omega is equal, and the frequency is equal to the absolute value of the momentum. Okay. Actually, this peak becomes more dramatic, as it should, is when n goes to infinity. Then, of course, you have a peak at omega equal to n, which is something which is what you expect from the usual dispersion relation, yes, because the energy, which you identify with frequency, is square root of well, mass is small, it's just square root of it's just the momentum, the value of the momentum, so the omega is equal to n. So these solutions, in other words, compared to quantum field theory in a flat space-time, now we have, in which you have these plane waves, now we have wave packets. So the effect of the zeta space-time is to replace, if you want to have states, you cannot construct this plane waves and do not satisfy equations because, okay, in other words, you have the momenta do not commute, yes? So in this case, so instead of plane waves, which have fixed, let's say, 4 components of momentum, in the zeta space-time you have wave packets. That's the crucial difference. So now, when we're considering scattering processes in the zeta space-time, they will look very similar to what you would see in Minkowski space-time when considering wave packets. Okay, so that's the most obvious thing. It's a complete obvious. That's what should happen. But anyway, so and usually when you do also the spectral decomposition for arbitrary values of momenta and masses, then you indeed peak, and then indeed you have a peak at the frequency which you identify with energy, which is related to the momentum n and mass, so the usual dispersion relation. Okay. So this is exactly what you should what do you expect? All right. So now let me go back to the construction of quantum states. So you start from the vacuum annihilated by vacuum annihilation operators, and you construct one particle states by acting with creation operators. There are states which are labeled by n, and of course you do it for a fixed mass. So in this way you can construct these states of Hilbert space, and you can show indeed you can construct now the symmetry generators, and you can find now that these states are really form a principal series representation, which means I can construct L0 from the quantum field, and I can construct all other Ising-Lowen operators, and you see that they really act like L plus, L minus, and L0, of course, the eigenvalue of L0 is n, but also L plus and L minus, they raise and lower n with the appropriate Klebsch coefficients, which are appropriate for this representation. Okay? So indeed, the states created from the vacuum by this quantum field form principal series representation. Okay? The same thing when you have in Klein-Gordon theory, for example, and Minkowski space-time, yes, when you act with creation and annihilation operators, you create states which are representations of the Poincare group. Yes? Here create representations of the Sitter group. All right. So the next thing, we want to construct the scattering amplitudes as measured by an inertial observer who is undergoing the geodesic motion on the world line parameterized with proper time. Okay, so that's what we want to accomplish. So what do you want to do? We have compute transition amplitude between in and out states. Where in and out states are these states which are from principal series representation. Yes? So this is the standard thing. Okay, you have to extrapolate these, and now there's a very important thing that now, okay, I'm working in the proper time of the observer. There's only time that the observer can measure, his proper time. Yes. So I have to evaluate, I have to take three states at the far future and the far past, and then extrapolate to, let's say, tau equal to the proper time equals 0. Okay, and I do it by using Hamiltonian. Yes. So now I have to find the Hamiltonian. But then the next thing. But anyway, these states, asymptotic states, are these states from the principal series representation. Okay, so I find Hamiltonian, I'll be able to construct this transition amplitude. Yes. All right. So here the story goes interesting. What is the Hamiltonian? Well, Hamiltonian is the evolution. It should generate evolution in proper time. Yes. And well, it is. Well, it's easy what it is, okay? So now if you take, and I can do it for specific for this observer, which is here on the red line, yes? For this observer, when I boost in positive direction number 1, I'll be moving here, the points here will be moved upwards, so I'll generate motion forward in the proper time. Yes? All right. So the boost operator is, in this case, the Hamiltonian is the boost operator. What's tricky about it, that on the other side, for the mirror observer, it will be this boost will be generating motion in the negative embedding time direction, but this is in positive proper time direction. So on both sides, the boost operator will generate motion in proper time, forward in proper time. Okay, so and this Hamiltonian, which is boosted somehow called modular Hamiltonian, that appears in various contexts, even when discussing like accelerated observers in flat spacetime. Okay, so now how to construct this Hamiltonian? So the question is how to construct this how to construct Hamiltonian from the in quantum field theory. The way to go is very simple. Now each generator goes together with the killing vector, yes, with the property. So there are 3 killing vectors. And then what you do, you construct the currents. So you can construct corresponding currents by contracting the killing vector with the energy momentum tensor. And then you have a conserved currents. And one of those currents, which is associated with the boosts, it will become the current, energy current. So its charge is becoming Hamiltonian. Okay? And I can construct it by following that path. I can construct the Hamiltonian. I can express in terms of fields. Okay? Now, this part looks completely very well known. Yes, that is what we have a free Klein-Gordon theory. And this Hamiltonian, of course, this is Hamiltonian density, spatial density integrating over over the angle on this spatial coordinate. So this part is completely standard. Then if I cause of interaction Hamiltonian, I would have to add something like phi cube or something like that. Yes. What is new and weird? That in addition, there is a factor which is sine of the angle, which means that the Hamiltonian density is positive for those guys and negative on the other side. And this is what exactly you'd expect, because the boosts on the other side move in the negative embedding time direction, which is what I want, which is in positive proper time direction. Okay, so the Hamiltonian is not. Hamiltonian is density is positive definite on one half of the jitter, and negative, and it's negative definite on the other side. But it's exactly what I want, because it will generate Hamiltonian ocean and motion along both geodesics. All right. All right, so now what I do to construct the S matrix, what I do, I just start from those asymptotic states and then follow essentially all steps which are very nicely explained in the, like, for example, in the book and the notes, lecture note of Sidney Coleman. I construct, I perform usual operations, which at the end boil down to the fact that you can write down this transition amplitudes as matrix elements of the 3 states with this time evolution operator given by this formula, which is the time order of the interaction Hamiltonian, this exponential, which is called Dyson formula. Okay, there's a standard formula now without tau. If it's t, then in Minkowski space, and you would think about those states, for example, as states with definite momentum, yes, and then this will be some interaction Hamiltonian, which will be like phi cube or phi to the 4th or whatever. Okay, and this matrix element just this transition amplitude will be given by the matrix element of this operator of the 3 fields. Okay, now for us, this interaction Hamiltonian. Okay, the important thing here is what enters here is this free Hamiltonian, which I identified before with the boost. And by using that, actually, by using, you can perform this computation. And what at the end, what you find, that this transition amplitude is exactly, is like a matrix element of this operator, which can be written in the same way as now this integral over the proper time can be replaced together. Okay, at the end, the whole thing boils down to integral over the whole space-time. And this is something, if this square root of minus g means, okay, if you forget about that, this is something which is called Dyson's formula. It's the one which is the starting point for any computation of transition amplitude, which you use. Okay, from that you can get Feynman diagrams, you can get everything. Yeah, this overall, this first of all, you first will integrate over all the sitter. Okay, and you integrate, okay, and here you, of course, you have an invariant volume. Okay, so that's the only thing, but now we integrate over all the sitter. So now you say, how does it know about, what about?
I remember, they have singularities. It's wave functions on the other side, yes?
No, yeah, no, so this is, I will show you how to come, I will show you some simple example, I can compute it for you. Yeah, okay, let me just anticipate your question.
Are they regular?
Oh, fine. What did you say? 5 minutes?
5 minutes left.
Oh, yeah, okay. All right, so then, okay, but I thought it was, okay, yeah, okay. So this is essentially the final result, which I can use now to compute transition amplitudes, okay? By the way, the S matrix, of course, is the Hermitian operator, this S matrix is unitary, okay? So the next thing that I want to do, I want just to test what I get from that. For example, I can take phi cube theory. Well, this is like and let's consider transition between, the states with different masses and different momenta, yes? Okay, like 3-point function. Then it's obvious, since this is like, this whole computation goes like, the same way as, if you will, considering wave packets, which means at the end, this amplitude and phi cube theory just overlap of the wave functions, okay? Of the wave functions. And but now integrated over, well, you integrate over a whole volume. Well, at the end, it boils down to integrating over some time variable, which at the end can be always transformed into this time and embedding Minkowski space, which I call T. And then, of course, spatial dimension. So I can write it this way. And then this integral over a spatial, well, over a spatial dimension of this angle will give you momentum conservation, yes, delta function. And here, rest will be this essentially overlap. Okay, you can perform Fourier transforms, and at the end will be overlap of those wave packets, the overlap of those spectral functions. Okay, now I told you that so this is the final formula. Okay. Now to test it, what do you want to do? Whether that gives you sensible when you get a sensible result, again in the limit where the momenta are large and masses are large. Yes, so if you are probing short distances and short time intervals. And then I told you that these spectral densities peak at the values of the frequencies with the frequency identified with energy related to energy momentum through this usual dispersion relation, flat spacetime. And at the end, you find when you take the limit, when, for example, n goes to infinity, you find that this amplitude, 3-point amplitude, is exactly a delta function, yes, which is exactly the thing that you find in flat space-time, okay, and with the proper normalization, of course, okay. So this proposal, whatever this way of this in this way, the S matrix obtained by using this generalized Dyson formula gives you something in the flat space-time limit, something which you want, okay? Which is all right. Okay, so what I can do, I'm almost done, because what I would do now, I would just essentially what I have here, the abstract of the paper, and which I put here as a summary, and you see that, okay, that exactly, I hope that now it becomes clear what I did. So I developed formulas for scattering in maximal de Sitter, symmetric de Sitter space-time. And then the quantum states were described by using representation theory of the Sitter symmetry group. And this Hilbert space is linked to specific class of geodesic observers. Okay? So there's no discussion who is, so I know who is, this is who is any observer in the Sitter spacetime will, okay, all these, here this symmetry, the Sitter symmetry links observers and links all these scattering amplitudes. And I told you that the way I construct positive negative energy waving function was determined the requirement that an observer's neighborhood show flow wave propagates with positive and negative frequencies. And then I showed this formula, which I call Dyson's formula, which you obtain, which is very similar to what you have in flat spacetime. And what is important compared to the flat case, the Sitter scattering amplitude describes scattering of wave packets with the frequency spectrum determined by geometry, completely determined by geometry. Okay. And then the frequency spread shrinks as the mass and momentum become larger than the curvature scale. And so asymptotically, these amplitudes agree with the amplitudes evaluated in Minkowski spacetime. What I explained here, okay, I used as two-dimensional the Sitter as a proof of concept, but similar details can be worked out in a four-dimensional physical the Sitter spacetime, and this is work in progress. Okay, so okay, that's essentially all what I wanted to explain. All right, thanks.
Thank you very much. Jacek,
Yes.
question?
But this is of course not the theory of aesthetics, because you calculate one process. What about propagators and stuff like this?
No, the propagator, that is more complicated, but there is a work on that because the propagator, I know what it is. Yes, okay, the propagator is the Tjordat product. As usual, you have to propagator is a Tjordat product of those two fields. And then you have to use, it will be some, you have to then, you can try to, and that, for example, there is a construction which was done by Jan Drezinski, for example, here. And some other people also have similar, you can construct these propagators. So the point is that you want to, these are time-ordered products, okay, of some functions. So what you'd want to do, you want to replace this time-ordered product by some integrals, like you do it, for example, in spacetime. The propagator, when you think it's 1 over k squared minus its integral, 1 over k squared minus m squared. This is much harder, of course, to do in the Sitter spacetime, but that is something which will be done sooner or later. Well, I don't know, you can, yeah. Okay, here there are no singularities. No, because it's one, because I'm doing it again, there's observer, I'm doing it, okay, I don't see any singularities, okay? So somebody else can see some singularity. No, it will be when I compute matrix elements, when this phi cube, there was no propagator. When I compute, for example, the if I compute the 4-point function and phi cube, I will have to include this Tjordat product of two fields, and that has to be done. But as in principle, I can compute it. Okay, but then again, the question with the propagator, of course, the propagator will not have a pole, and when the momentum transfer is the mass, it will something which will be different, and that's why the soft behavior, of course, at high energies, and high masses, I will get the same thing as in flat spacetime, I have the same amplitude. But when you go to lower energies or lower masses, you will see something new. And the point is that now I can compute what it is. Okay, so for example, if I have a soft photon, there won't be the usual infrared singularity, yes, because in the Sitter spacetime, you have there is a large distant cutoff, yes, which is related to the curvature, yes. So there won't be,
This I
you agree. So
but extra singularity because of the opposite point. They are not regular.
yeah, but well, again, the question is whether it leads to any, the bottom line is the transition amplitude, okay? And it shouldn't have any singularities. Yes, you should have the singularities, only like kinematic singularities you expect, and so on and so on. Yeah.
know what are the correct on-shell normalization conditions for this category?
Now here I even didn't touch the loops, okay? That would involve propagators, and that is again something which is still far ahead. Okay, that's the what I want to understand first, even at the T approximation now with including propagators and so on, I will be able to see, for example, a soft behavior in flat spacetime. For example, you have something with soft theorems which tell you what is when you can take one, for example, photon in QED. If you take a very soft, then you hit singularities due to the presence of the usual propagators and so on and so on. Okay, I don't expect this type of singularities here, but I expect something different. And then when I compute it, and then for that, another place where I see that there are other particles which are even more interesting for which this can apply. For example, you know, the neutrinos are some neutrinos can be very close to zero mass. So neutrino physics could be affected by cosmology. But in this framework, I'll be able to compute everything. I'll be able to know how I will compute those effects. The question is whether they can be observed or not. Yeah. Yeah, proper time. Yeah, this entire yes, correspond to yes, proper time. So asymptotic states are exactly defined not for everyone. Asymptotic states of the observer at the infinite past and in the future, which is in proper time. There's no global. There's no like. In other words, it's not that. Yeah.
Yeah, that's right. Yes,
Yeah.
Global way. Penetrating all the. For example, the effect outside the cosmological crisis correspond only to space.
Okay, I try to avoid going into that. Okay, the point is that what is the role of the other side? Yes, of the second half of this other side. The way you have to think, the way you have to think about this whole scattering processes, anything like that, is that what happens on the other side essentially mirrors other half. The probability that you construct correspond to something something happening on this side, but the same thing happening on the other side. So that essentially the physical amplitudes and physical probabilities you compute them. Essentially the recipe is to consider the other half as a mirror image. There's no independent thing happening. And the same thing when you have, for example, Dirac theory, you talk about, let's say, positron moving spacetime, talking about Dirac C, yes, if you want to reduce relativistic quantum mechanics, yes? And nobody asks you about, nobody bothers you about the Dirac CS. Okay, nobody asks, for example, what's swimming in Dirac CS, so to say. So it is not independent. It's essentially CPT image, which runs at the same time. There's no separate things on there are no separate thing on the other side. They do not talk. They could never talk. Yeah, I mean, if you are here, if you are now given, then you see from Penrose's diagram that okay, you could have never communicated with the other side. Yeah, okay, well, but I'm talking about, again, everything here is happening, everything, what I was doing, happening for observer at a given moment of time. So there's one observer who sits at, which I drew in the middle, at the throat. No, I mean, it could have computed, but the way okay, when you compute these transition amplitudes, you extrapolate with these boost operators, and then, okay, that it takes into account. But the way to think about it, if you want to have some intuitive picture, is thinking that the other side, there's always for a given process, there's a mirror process happening. You will never know about it, and you don't care about it. Okay, it just
Sorry, I need to stop here
Yeah.
because we are running out of time.
Okay.
So please continue. And thank you very much
All right, good.
for a nice talk.